Hello guys, this is Dean Palmer. I will be talking about the Amazon Locker problem. This is by JJ Bell and Dean Palmer, so let's get right into it. First, we have 300 customers that all need to be serviced. The constraints are that each customer cannot exceed 30 kilometers from their assigned locker location. Now, we do not need to build all 30 lockers because some of them might not be worth building based on the cost to benefit ratio. So the objective is to minimize the cost from building lockers with the distance cost from each locker to customer. So the assignment is to take 30 locker locations and decide if they are worth building or not. So here's a picture of a 2D graph of all the locker locations that are red dots and all the blue locations that are customers. So you can decide that little yellow dot in the top left hand corner is about the range. So the 5 parts for this problem are create the simple Excel model. We're also going to create a MIP formulation just in a Word document. We'll create an MIP formulation in IBM. We'll create a meta-heuristic in MATLAB, and then we'll compare those results. So here's the Excel. As you can see here on the first left-hand side that we have 29 and 29 both for the first two lockers. That makes it so we only decide to make one locker and save us a lot of money. The minimum cost is about $50,000. And then for the other side, we have one that's outside of the range at 31. So we decide we have to make both lockers because we need to make locker 2, which is almost double the cost.
Okay, so for our MIP formulation, we have three components: the decision variables, the objective function, and the constraints. Our decision variables are x of LC and y of L, where L is denoted for the lockers and C is the customers. Our objective function, we have to minimize the cost of locker installation as well as the cost of the traveling distance for each customer to that locker. As for our constraints, we have x of LC is less than or equal to y of L. This is each and all customers need to be assigned to a locker. X and LC and y of L are binary. They're also non-negatives. D of LC is our distance matrix. The customers are to have a max distance of 30 kilometers and no more than 30 lockers are to be assigned total. Okay, so for our IBM model, we have the customers and lockers as string variables. The Boolean variables are x of LC and y of LC, where the lockers and customers are denoted. And we have the int variables of the max lockers assigned, which is 30, and the lockers assigned to each customer is to be 1. The maximum distance for each customer traveled is 30, and the float is the distance matrix. And once again, we are supposed to minimize the total cost of the customer's distance traveled as well as the locker installation. And then the note below that was our constraints. This is our data file. Customers and lockers are denoted as strings. And as for our distance matrix, we tried 4 different ways that you could see commented out to import the data, but we were unsuccessful in doing so.
For our meta-heuristic, we use the genetic algorithm. At the top, we have our function, which is 100 times x for a penalty and x times 50,000 for a penalty. We have it ranging from 1 to 30, saying that it has to be in between 1 to 30. We have a random generation coming into the equation with a maximum generations of 100 and our population size of 300. We also have a 95 chance of getting a crossover probability and a 5% chance of mutation probability. So for our max gen, we have a for loop. We have the crossover probability, which is a matter of just switching two numbers that are next to each other. These all are run through if loops, and we also have a mutation probability, which is one number just getting totally switched with another number. Doesn't matter where it is. The mutation is less likely because it usually doesn't make as much improvement. So for our generation of initial population, we also have that function, and that runs through the function evolve, which goes through the global function, which pretty much just runs everything over and over again until it comes up with a maximum solution. But since the maximum solution was negative, that should produce a minimum solution. The float point decimal, that allows our answer to be a final decimal. So for this one, we have the function, which is a crossover. So that runs through all of our crossovers, and every time we use one, it puts -1, so we don't use too many crossovers. And the same thing is done for that of the function of mutation.
So comparing our results, IBM, we were unable to import our data. although it is faster and gives us the optimal result, MATLAB with a genetic algorithm is slower and gives us the feasible result, which we were able to obtain was 798,000. From previous projects, we were able to observe that the OPL should be about 816,000. As for our conclusion, we had successes and failures throughout the entire project. Our successes included the IBM's model, the Excel model, our formulation, and the MATLAB, and our failure included importing the data. What we learned from this, we learned how to use software to solve everyday problems such as Amazon locker problem, and we learned how to use time management and how to work together as a team to tackle a project beyond our coding capabilities.